Hey guys, welcome back to my channel. I hope you're feeling great today. And today we have video number 6 already of our MATLAB series, and we are going to talk about special values and operations. That means we're going to have a quick look at real and complex numbers in case you need them for your calculations and how you can write them inside of the MATLAB environment. We'll talk about bracketing a little bit, how you use brackets properly. Also talking about exponential function, the logarithmic function, but also have a quick look at the operators like bigger than, equal to, less than, etc. Last but not least, we are going to have a quick look at the so-called NaN, which stands for not a number value. So I would say without further ado, let's jump right into our MATLAB environment and let's go.
Hey guys, and welcome back in the MATLAB environment. So in the first section we are going to have a look at real and complex numbers, and I will quickly show you how you can type in a number that has a real and a complex part. So we just make a small example. Let's say this is our first variable and we say it has one real part and two imaginary parts. Now if we execute this by clicking F5, you can see that the variable a has this one real part with 4 digits after the comma, and two imaginary parts also with a precision of digits after the comma. I will talk about the precision and the amount of numbers you can see after your separator in the next video, so make sure to stay tuned. So here we can put a semicolon at the end to suppress the output, and I will do a second example for you. You can also define a second variable and we just call it 3j. So that's the second possibility. You can indicate imaginary parts by using either the I here or the j. So if we execute this by clicking F5 again, you can see variable 2 has 0 real parts and 3 imaginary parts. So as you might have seen in the last video, to avoid confusion, and maybe we have defined I beforehand, there might be some troubles later on in the code, and to avoid this we usually put a number in front of our I to really indicate that this is the imaginary part. Moving on to section number 2 with pi and e. Let's say your teacher or lecturer gives you the exercise to calculate the, let's say, area of the circle. So we say area of the circle is like pi times the radius squared, as you might know. So let's say we don't know pi and how to call pi, and we would write something like this: 3.14 times radius times the radius. Of course we have to define the radius right now. Let's say the radius here is 10, and let's just call this radius area of the circle 1, mark this, and then area of the circle 2. But now we type in pi to be a little bit more precise, and let's just see what the output says. Let's just suppress this to avoid confusion. Click F5, and you see that the area of the circle 2 is way more precise than the first one, because the first one was just an approximation. We used the 2 digits after the separator for pi, and now we're using pi here and call the value actually from MATLAB to calculate the area of the circle. So that really makes a difference, as you can see. Now talking about the Euler's number e, you can call the Euler's number by typing the function exp and not using the caret symbol. Let's say e to the power of 1. That would not work because exp is a function and it wants some input arguments actually. So let's say if we want e to the power of 1, we can type this here. Let's just suppress the output for a moment. Now exp1 is 2.7183, that's correct. And let's say you want to have another number exp to the power of 10. That would be a bigger number, 2.2 to the power of 4 times 10 to the power of 4. This e means times 10 to the power of, and then this 4 indicates what this power actually is. So also suppress these outputs. Of course you can find the M file as always in the GitHub repository, so no worries about that. Moving on to not a number. So how can we create something like this? Let's say we create a variable 3 now, and that is 0 divided by 0. And we execute this, you see? That's not defined, that's not a number. Now what you have to keep in mind is that sometimes you can find values like these, NaN, in an Excel spreadsheet, and if you import this Excel spreadsheet you have to find a technique to substitute these NaN values. That's very common in data science. let's say you have values that have these NaN values, and there are special techniques. Let's say you take the average of the column or row and substitute the NaN numbers by this operation or this technique that I have just mentioned. Moving on to decimal powers. So as you have seen on the top, we have had this E in the output. So I'll show you some examples just to show you another trick. You can also type in a number that's like this, 0.12458. Instead of writing this, you can also use a shorter version, which just neglects the 0, and this is also valid code right here. So if we would execute this, so press the output here, you see it prints the number with a 0 in front. It saves a little bit more time. Actually, I don't like this technique or this method or habit. I would just write a 0 just to be sure. And of course, MATLAB is an American product, so you would have to use a dot as a separator. So Germans might accidentally use a comma. So I'm guilty of that because I used so many commas and then I tried to find the mistakes. And MATLAB tells you, fortunately, that the delimiter or separator has to be a dot rather than a comma. So in section 5 we talk about the biggest and smallest value MATLAB can represent. So what you have to know is that, let's say, MATLAB always calculates in double precision and it calculates in types of double. And according to the IEEE standard 754, MATLAB can go from values to 10 to the minus of 308 to 10 to the power of 308. And you can actually, because you probably didn't remember this number right now, you can call these values by calling real min and real max. Let's just print them out and see what they are. So this is the smallest number, and this is the biggest number MATLAB can represent. What about the smallest number though? We can call that by calling the abs function, type in a 1, and it would give us the smallest number MATLAB can represent, which would be 2.2204 to the power of minus 16. Now, why is this important? It's very important to know actually. I'll show you an example why this is very important. Let's say we have a calculation that says 10 times 1 minus 0.9, and this is also subtracted by 1 again at the end. And let's just call this var5. var5. Calculating this in the head is very easy. It's 1 minus 0.9, which is 0.1, and 0.1 times 10 is 1, and 1 minus 1 should be 0, right? But if we execute this code right now, you can see that var5 is actually not 0, but a very, very small value. And that is because MATLAB, or computers in general, calculate things to a specific or certain precision, and it cannot represent this 0.9 or 0.1 exact. And that's why you have this rather surprising result right here. Yeah, I have seen people in the past do this, like if they do a conditional loop, let's say if this expression here, say if this expression is equal to 0, and then do whatever, then they put their code inside of here, code here, and then the tab end. And this condition would never be true because, as you have seen, this code, this part of the code or this code snippet will never be equal to 0. So what you can do though to overcome this is, let's say you write a different statement that is like this. If, let's just suppress the output, grinding my gears a bit. You can write it like this. If, let's say, this is smaller than a threshold, an epsilon that you define, or a specific number, and then put your code here, and then the loop would end. And that's a better practice because you know this statement would never be real, and you just define a threshold under which this condition has to be, or just depending on your case, just to make sure that you understand this and know that MATLAB makes small mistakes because it only can work up to a certain precision, and then there's a certain limit to that. On the one hand, we have equal to, which is this sign, so two equal symbols. Then not just make a section, but just make a comment. Then we have not equal to, which is like this tilde symbol and this equal sign. Then we have bigger than, which is this sign, smaller than with that sign. Then we have bigger or equal than, that would be this and an equal sign. Then we have smaller or equal to, actually, that was English mistake by me, equal to, and equal to sounds better, right, would be this. So what does it actually mean? Let's just make an example. Let's say we want to check if 1 bigger than 5. Let's just also comment this by marking this and clicking Ctrl R to comment, so that we don't get an error. And what does it give us here by clicking F5? It gives us a logical value, as you can see, which is 0. So what does that mean? So if we do operations like these, we get either a 1 or a 0. These are Boolean values, so-called Boolean values, and 0 means false and 1 means true. So in this case, MATLAB tells us, okay, this is actually not true. That's why we have a 0 right here. Let's just call this var6. I'm just saving it to the variable right now. Let's just check another variable, variable 7. Just call it 5 bigger or equal to, let's say, 4. What does it say now? Suppress this here. This is 1, because this is true, because if 5 is bigger or equal to 4. So we can actually write that these are the so-called comparison operators, and we can also do like the logical operators. I just want to mention these. I will use these in a future series, by the way, anyway, if we code a little bit more, but I want to make sure that you have a small introduction to these as well. So now going to the logical operators. So for the logical operators, we have several options. We have these two AND symbols, which stands for AND. Then we have this two bar symbols, which is OR. Then we have this tilde symbol, which is NOT. And then we have this so-called XOR value, which stands for XOR. So you can find all information about that in the, of course, in the MATLAB documentation, but I'll just give you a small example. Let's say we want to check if what is variable 8. It should be checking if x equal to, of course we have to define x beforehand. Let's just say x equals to 4. So x bigger as or equal to 2, and it should check if also this x value is smaller or equal to 6. So what would that give us? It would say 1. So let's just check for a moment. 4 is bigger or equal to 2. That's correct. So this is a 1 here. This is true. And it should also check if 4 is smaller or equal to 6. This is also true. And true gives us true. So if you don't know how to memorize this, it's very easy to memorize actually. You can think of that with some circuits actually. So you can find very nice pages where you can find nice mnemonics for the logical operators. For instance, here's the AND logical operator that we just used, and you can imagine this A was our first expression, this B was our second expression, and now we say, okay, if A and B is true, so both circuits here are closed, so this whole circuit is closed, then this is true. So the light would blink or whatever. Now if A is closed and B is open, you would see no light, right? Because there's no current going through this wire, so it would not be closed. The same goes if B is closed and A is open, so there would also be no current going through the wire and you would see no light. But also if both are open, you would also see no light. So this is also out or false if you want to imagine it like that. So I hope that helps you a bit, and you can find other circuits that explain the OR logical operator, for instance, or the NOT operator. Moving on to section number 7, which is trigonometric functions and how you can call trigonometric functions. It's very easy. So you can use the function sine, cosine, as well as the tan function to make use of all these three trigonometric functions. And as we call a function, we have to put the argument inside of our brackets. Let's say we want to have the cosine of 0, and we want to put this value inside of our variable 9. What does this give us? It's 1. So that's true, you can check that by yourself. var 10, let's say that's the sign of pi, and that would be this value right here, which is also true. And we can also define, now if you want to use the inverse functions, there are also functions for this. You can use the arcsine or arccosine if you want, and that's just by putting an a in front. Let's say type in a cos of 0, what would that be? Just in case you need them, you can also call the hyperbolic functions of the arguments we just used. So you can say the hyperbolicus of the sine function, and then type in your argument. We just comment that one here, and you do it with the other expressions I've shown you as well. So moving on to the next section, and we are almost done, so bear with me, you're almost through it. The exponential and logarithmic function. So for the exponential function I have just shown you beforehand, you can just type in x and then the argument, and then we just print out the value, so we have that covered. And for the logarithmic function, you can also just type in log. This is actually the natural logarithm, so you can type in a value for that. Let's just type in 1, and that should be 0, hopefully. That's the case. Then if you want another basis of the logarithmic function, you can use log 10. Let's just type in the comment. You can also use log 10 or log 2, depending on what basis you want for logarithmic function. Now, a very interesting topic as well. We will talk a little bit about bracketing right now and why this is important. Let's say we have a number, and the actual thing we want to print out is, let's say, 3 to the power of 2 plus 5. Actually, we want this to be 3 to the power of 7, but somehow we have to use this, let's say, but we forgot brackets. Or we'll make an easier example, 2 plus 1, to make it a bit easier. So what will this expression give us? Let's say if we have 3 to the power of 3, it should be 27, right? Okay, let's just execute this and see if we are good to go. Okay, that's bad. That's actually 10. So what happens here? It first calculates this exponential operation and then adds a 1 on top of that. So 3 to the power of 2 is 9, plus 1 is 10. If we put this in brackets, what happens now? It will change to 27, as you can see, because we have used brackets. We first want the 3 to be alone, then use the caret symbol, and then the exponent of 3 to have 3 to the power of 3. The same can also happen if you calculate something like this. Let's say you have a fraction and you say 1 plus 4 and then divide the whole thing by 4, whatever. If we execute this, this is 2. But that's not correct. It first calculates 4 divided by 4, this is 1, and 1 plus 1 is 2. What we actually wanted to have is, this is the numerator, and this is the denominator here, this 4. So what happens now is we don't get this 2, but we get the 1.25, which is the correct value. So always make sure to intelligently and very meticulously use brackets when working with bigger formulas, so that makes sure that you can avoid problems.
So this was video number 6 already of our MATLAB series. I hope that you enjoyed it. As always, make sure to hit the like button, and as always, you know the procedure already. Share it with your friends, hit the notification bell, and subscribe if you haven't already. In the next video we are going to talk about formatting and type conversion. That means that we have some special output, a special format. That means we see 4 decimal places after our separator, in our case the dot, and we can change that actually inside of our MATLAB environment, which we will see in the next video. But we will also talk about type conversion inside of MATLAB. That means that we have specific types that MATLAB offers us, and we will have a look at how we can convert one type to another type and vice versa. So make sure to stay tuned, and I would say see you in the next one. Peace!